Hello, this is Miraj Patel, and today we're going to be finishing up Unit 3 by talking about the last model of an atom, which is the quantum mechanical model, and we're going to be talking about electron configurations and how to do them. And so, from the last few videos, you can see these models and how they evolve. So first, before the Bohr model, Rutherford made a model with the nucleus and then the electrons floating around. Then, in 1913, Niels Bohr made this model, the Bohr model, which has a proton in the center and electrons in perfect rings. But there's one more model, and the reason why they have this new model is because electrons, like this propeller, are moving so fast it's equally likely of being in this blur or around the atom. So, like, same thing, electrons are always spinning super fast around the nucleus. So electrons are equally likely to be in this location versus this location or this location, just like this propeller. And so you cannot tell exactly where the propeller or electrons are around the nucleus. So that's the whole principle why we have this quantum mechanical model, and Erwin Schrödinger and some other scientists developed this. And so basically it shows the most probable locations of electrons. So the area where there's a lot of black dots, that is where the electrons are more likely to be. And then the lighter spots, that's where electrons are not likely to be. So notice how there's one ring here, and then there's a second ring all the way over here, and they're a little darker than the other ones. And then the equation describe electrons as waves of motion. They're not little electron particles moving around, they're waves of motion. So, and then same thing, pretty much the electrons are visualized not as a particle in the same location, but as but its mass and charge are spread in like a standing wave. So it's a wave going around the atom. So that's how they interpret it as. And a Bohr model shows electrons orbiting the nucleus like planets around the sun. And then de Broglie's model shows a wave in orbit. So pretty much you have waves going side to side and up and down. And then there's a quantum mechanical model which shows little dots in clusters where electrons are more likely to be around the nucleus. And pretty much the electrons are in a 3D cloud and of orbits of wave equations and probability. And so this is an important principle to know, that energy levels have sublevels and different shapes. So this diagram shows the sublevel. So for ring 1 you only have one sublevel, but for ring 2 we have two sublevels. Ring 3 we have three sublevels. And then this next picture shows the shapes of the different orbitals. So the first orbital is a simple circle, the second orbital is this larger circle, and these little flower petal like things. And the third orbital includes everything, so it has all sorts of space inside. And here are some atomic orbitals, or 3D regions with high probability of electrons, and there's four types. S orbitals are the first kind, and they're simplest. Then there's p orbitals, sp, and then d orbitals, and f orbitals. And so simplest is S is just a sphere. P orbitals are dumbbell shaped, so they have two ovals with the center at the or the point where they're touching at the nucleus. And then d orbitals are four little ovals, and they also touch at the nucleus. And then F has more than four orbitals. They may have 8 and 6 or whatever. But the two important ones you need to know are S and P. And so this slide shows the development of the model. So in 1803 we had the Dalton model, which didn't describe much. about the arrangement of protons and electrons. Then we have the Thomson model, which he discovered the electrons. Then we have the Rutherford with the nucleus in the center. Then Bohr developed the idea of energy levels, and then the quantum mechanical model in 1926 was developed after thinking about how electrons are not just in a few spots, they're all over the electron cloud. And they also have these shapes inside, these different orbitals, s, p, d, and f. And so here's a quick quiz to see what we learned. So, first question, what does the quantum mechanical model describe about atoms? A, the probable locations of the electrons in atoms. B, the precise locations of electrons in atoms. C, the number of electrons in an atom. Or D, how crazy chemistry is. It's not C or D. They don't show the number, and then D is just ridiculous. B, the precise locations of electrons in atoms. The whole point we have the quantum mechanical model is because we don't know where the locations are, because electrons are moving so fast and they're so crazy and they move out of control that we can't like define exactly where they will be, so like a propeller. So the answer is A, because it shows probable locations, because the whole point is electrons are so fast that we don't know exactly where they are, but we can figure out the general area or probability of where they will be. So question number 2, what do orbitals s, p, d, and f tell us about the sublevel electron? The amount of energy in each electron, A. B, the number of electrons in each sublevel. C, the shape of the region they occupy. Or D, that my brain feels mushy now. D is just a no-brainer. And B, the number of electrons in each sublevel. It doesn't tell us a number. If you remember, S, P, and D, F just showed the shape of the orbital. So S was a sphere, P was a double dumbbell, D had 4 O's, and F had about 8 or 9 Oreos. And so it shows the shape of the region they occupy. So the answer is C. So moving on to the next PowerPoint about electron configuration. And so electrons have different energy levels like we talked in the last PowerPoint. So there's an s orbital, which are spheres, and then p orbitals, which are these dumbbell looking things, and then d and f. And they also have different sublevels. So that's why 1s has just a sphere, and then 2p has the 2 orbital has the s orbital and a p orbital. So these are different sublevels. So how do electrons fill these orbitals? And so how do electrons, organize themselves? And so the electron configurations are the location of electrons in different orbitals. And there's 3 principles to describe electron configuration of any atom. They're the Aufbau's principle, the Pauli's exclusion principle, and Hund's rule are 3 rules that we use for electron configurations. And so this is an example of an electron configuration, but this is blank. It doesn't have any electrons in it. And the nucleus is supposed to go here, and so imagine this as a little cross section of the ring, so like the rings are floating around like this, and these are the different likelihoods. And so there's 1s, and then 2s, and 2p, and 3s, 3p, 4s, 3d, and then 4p. So these are different energy levels. And on the periodic table, this shows us the different energy levels on the periodic table, where you can find them. So first we have, let's explain the rules before we start. So before we begin, so these arrows represent electrons. So in 1s we have 2 electrons, and then 2s we have 2, then we have 2p, and then 3s and 3p. And Aufbau's principle is the idea that we build from bottom to top. So we start with 1s and move up to 3. So we only start from 1, then we go to 2, then we go to the next level, next and next. And so we have these arrows, and one goes up and one goes down. Same thing, one goes up and one goes down. And pretty much Pauli's exclusion principle is the idea that electrons on the same orbital have opposite spins. So an electron in the same box, the arrows have to face up and down. Then we have the third rule, and so this has to do with filling out these boxes. And so notice how in 2p we write all the up arrows before we start with any of the down arrows. And same thing with 3p, we write all the up arrows before we go with down. And that's Hund's rule. We have to start with up, 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 or down, down, down. Whatever you start with, you have to continue with the boxes before you can add a second one. So E's pair after one in each same E orbital. So just think about how if you're riding a bus, everyone sits in the single seats, and then eventually people will have to start doubling up. So just think about strangers on a bus. They all sit by themselves until they're all filled. And this is actually how you do electron configurations. We just talked about the rules. And first, you have to, find an element. So we're going to do phosphorus, which is number 15, which is all the way down there. And so basically, we have to count all the boxes before we get to phosphorus, or until we get to phosphorus. So first, we start with hydrogen, so number 1. So, and as we go, we have to fill out these boxes with arrows of electrons. So 1s, we have 1, 2 boxes of 1s. So we put 2 arrows, one upwards and one downwards, because that's one of the rules. We have to make the arrows alternating, so one up and one down. Then after we pass helium, we go down to lithium, which is in 2s, and then we have beryllium, so that's 2 boxes right there, so 2 arrows right here, one up and one down. And by the way, as you're doing this, you have to write out everything. So you write first you write the category, so 1s, and then the exponent tells you the number of boxes you pass by. So this would be 1s2 because we passed by 2. So next we have 2s, and we have 2 elements here, 1, 2. So up here we would write 2s2 because we passed 2 boxes. Then we go to 2p, and there's 1, 2, 3, 4, 5, 6 boxes. So again, we first write the electron. So first we have to do all the up arrows, then the down arrows, like this. And then we write 2p6 to the exponent to the 6 because we passed 6 boxes. Then we go to 3s, and we have to pass 1, 2 boxes. So we write 2 arrows right there and write 3s2. And then we go count up to phosphorus. So there's 1, 2, 3. So we stop at 3 arrows. So we have to write 1, 2, 3. And we have to continue doing up before we start down. So there's 1 arrow in each box. And then we end it off with 3p3. And so that is how you do an electron configuration with the notation and this box diagram. And valence electrons are the electrons in the outermost or highest energy level, and these numbers, or the coefficients of these letters, represent energy levels. So this is 1, this is 2, this is 3, and so is this. And so to find the number of valence electrons, you have to look at the number with the highest coefficient. So in this, there's 1, 2, and then 3. So 3 is the highest. and we count the number of electrons, which are these little exponents, so there's 2 and 3. So phosphorus, like I said, we look at the highest energy level, and or also we can count the arrows, 1, 2, 3, 4, 5. Same thing here, there's the highest exponent is 3, and we look at the exponents. So the number of valence electrons is 5. And now we're going to do another one for krypton. And so krypton is this box, and same thing, we have to count all the boxes. So the first box, we have to pass 1s. So 1s, there's 2 boxes, so it'd be 1s2. Then we go to 2s, and we still have to pass 2 boxes. Then we go to 2p, and there's 6 boxes. And then we go to 3s, and there's 2 boxes again. We're still not there. 3p, there's still 6 boxes. So 3p to 6. Then we go to 4s, and there's still 2 boxes, so we fill up that box. Then we go to 3d, and there's 10. There's 10, and this is weird, but 3d goes after 4s, and so pretty much when you go down the periodic table, it goes the exact same order you see it as. So if you see 4s, then you see 3d, then 4p, then 5s, then 4d. And so the D block is pretty weird because it goes after the higher numbers s. So 3d goes after 4s, 4d goes after 5s, and so on and so on. And so this still counts as a third energy level, but this is just weird how they place it. And so there's still, we have 3D filled, so we can fill up all those boxes. Then we have 4P, and we have 1, 2, 3, 4, 5, 6 boxes, so we fill up the 4P box. And we are done with Krypton's electron configuration. And the number of valence electrons, or the electrons of the outermost energy level, is gotten by looking at the highest energy level. So in this one, 4 is the highest, so you can look at here, or you can look at the exponents of the highest coefficient. So 4 has 2 electrons and 6 here, so 2 plus 6 is 8. And same thing here, you can count all the ones in the 4 boxes, so there's 1, 2 here. Don't count 3D because this counts as a third energy level. 4 again, so 1, 2, 3, 4, 5, 6 plus 2 is 8. So krypton has 8 valence electrons from there and from the notation over there. And we're doing one more problem, but this time we can use a shortcut I'll show you at the very end. And so write the full electron configuration for gallium, Ga, with the atomic number of 31. So again, we have to count through all the boxes, so 1s2 because there's 2 boxes. Then we go to 2s2 because we passed 2 boxes. Then we go to 2p6 because we passed 6 boxes. Then we go to 3s and we passed 2 boxes, so 3s2. Then we go to 3p, past 6 boxes again, so 3p6. Then we have 4s, we still pass 2 boxes, so 4s2. Then we have 3d and we pass 10 boxes, so 3d, 10. And then we have 4p and we only have 1 box to get to gallium, so we have 4p1. Or you could have wrote this argon, so just write argon in brackets, which is right here, and then continue on the pattern from there. And the reason you can do this is because these are noble gases, we can just use the last noble gas before we get to the element, and then we just continue on the pattern after the noble gas. So you could have just wrote argon, and this abbreviates for all this, and then we just continue the pattern. So 4s, we write 2 because we have to pass 2 after argon. Then 3d, we write 10 because we passed 10, and then same thing, 4p1. So if we did if we do any element, you can write the last noble gas before you get to the element and then just continue the pattern. Because if a scientist had this, they just can, do the argon configuration just to make it shorter. So argon is all this, and then we just write the additional elements to get to the new one. And this is called noble gas core configuration because the noble gas is used to abbreviate this whole core of this whole notation, electron configuration. And valence electrons are electrons in the highest energy level, and so phosphorus, you can look here, and has 3 energy levels, so 1, 2, 3, so 3. The third energy level, there's 2 electrons and 3, so there's 5 electrons total. And even if you did the noble gas core, we can still get the same answer, so we still get 5. And on the periodic table, if you look, the columns on top of them, they say 1, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Those tell you the valence electrons, but those only work for the columns with A on top. So in the middle where the transition metals are, it doesn't work there, but it works for the column with helium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and helium. So the valence electrons is the same as the little A number. So phosphorus is in 5A, so it'll also have 5 valence electrons. And the Lewis dot diagram shows the valence electrons for each atom. And so you first write the atomic symbol in the middle, and then you first fill 1 dot, and then you come back around. So you first start here and write 1 dot. So you first fill up that dot, and then we can continue over, and this is what you get. So you fill up this dot, this dot, this dot, this dot, and then you can double up. Well, it doesn't really matter, so as long as you have 5 dots shaded in, that's how it's supposed to be. It can be 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, but this is the technical rule. But on the test, if you see 5 dots filled in, just don't mind the way it's shaded in. And then there's another one, bromine, and so we're going to do the Lewis dot diagram for this one. And so see here, you can write the noble gas notation, so notice how much shorter it is. And to find the number of valence electrons, we look at the highest coefficient, so it's 4. And then we count the electrons, which are the exponents, so 2 plus 5 is 7. Same thing here, even with the noble gas abbreviation, there's 2 plus 5 is 7. So valence electrons is 7, and this also happens to be the group number, so it's 7A, so it has 7 valence electrons. And then the Lewis dot diagram is BR in the center with 7 dots shaded around. And here's a quick quiz to see what we learned. So which element has the following electron configuration? A, calcium, B, neon, C, sodium, or D, magnesium. And these are Lewis dot structures or diagrams, and these show the valence electrons. And if you want to match up which one has the correct valence electrons, you would just look at the highest coefficient. But here we have 2 answers with the same number of valence electrons, so we have to figure out how many electrons it has total, not just the valence electrons. So this element has 2 here, plus 2, which is 4, plus 6, 10, 12 electrons. And the number of electrons is the same as the number of protons, which is the same as the atomic number. So this element has an atomic number of 12. And so if you look on your periodic table, element number 12 is magnesium, so the answer is D. And you can tell this Lewis dot structure is correct because Magnesium is under column 2A, and this has 2 valence electrons. And so same thing, you can figure it out. We just talked about this. It has 2 valence electrons because it's under 2A. And write the electron configuration of atom of oxygen. And so first we have to go on the periodic table and find oxygen, which is all the way over there. So we count the number of elements we have to pass. So 1s we pass 2, so 1s 2. Then we go to 2s and we pass 2 more. And then we go to 2p and we pass 1, 2, 3, 4. We have to go in 4. And so the answer should be 1s2, 2s2, 2p4. So the answer is C. And how many valence electrons are there? Well, after calculating this, you can just look at your configuration. So look at the highest coefficient, which is a 2. 1 is lowest, and then there's 2. So look at the exponents, which is a 2 and a 4. So we add up 2 and 4, and we get 6. So this has 6 valence electrons, and obviously, if you look at oxygen, above it is 6A, so it also has 6 valence electrons. You can just tell by looking at the periodic table instead of doing all this. And this picture just shows all the different orbitals. So notice how there's S, P, D, and F of all the elements on the periodic table. That is it for today. Now you are done with Unit 3, and the next unit will be Unit 4. And I hope this helped you learning about electron configurations, and I hope you have a good day, and we'll see you later.